You know how your phone can recognize your face? Or how a self-driving car just knows how to navigate a busy street? It really does feel like magic, doesn't it? But it all comes down to one thing: teaching a machine how to see. And today, we're going to pull back the curtain on that magic.
But that leads to a much, much bigger question, right? Can a machine really learn, like truly understand what it's seeing? Or is it just, following some super complex set of instructions? That is the exact idea we're going to unpack.
So we're going to start with a challenge that, honestly, a toddler could solve in a heartbeat. Just telling the difference between a kitten and a puppy. Easy, right? For us, it's total instinct. But for a computer, well, that simple little task is the start of an absolutely incredible journey.
Okay, so let's frame this whole thing like a quest. Our mission, should we choose to accept it, is to build an AI that can actually solve this challenge. And this right here, this is the first and honestly the most important step in any AI project. You have to clearly define the problem. There's a name for it. It's called problem scoping.
All right, so here's the first major hurdle. When a computer looks at that photo, it doesn't see fur or whiskers or a cute little nose. Nope. It just sees a massive grid of pixels, and every single one of those pixels is just a number. So that adorable picture of a puppy? To a machine, it's nothing more than a giant spreadsheet full of numbers. And that is the fundamental challenge we've got to overcome.
So how in the world do you bridge that gap? How do you get from a spreadsheet of numbers to, puppy? Well, the answer is data. Lots and lots of data. And I'm not talking about a few dozen pictures here. We need thousands, maybe millions. Just think of it like the textbook our AI model's going to use to study for its big test.
And in the world of AI, that textbook has a name. It's called a dataset. It's just a big, organized collection of examples. So for us, that means tons of pictures of cats and dogs. This dataset, this becomes the model's entire universe. It's everything that we'll ever know about the world.
And just so you know, that study material doesn't always have to be images. Data can also be superstructured, kind of like the spreadsheet for housing prices. You've got neat columns and rows for stuff like income, house age, number of rooms, all that. But here's the key. The basic principles of how the AI learns, they're exactly the same whether it's predicting a house price or identifying a puppy.
Okay, so building an AI might sound like this chaotic, messy thing, but it's really not. There's a very clear, structured path that everyone follows. It's called the AI project cycle. Think of it as the roadmap that data scientists use to get from just an idea all the way to a working model.
This whole cycle really breaks down into 4 main stages. We've actually already talked about step 1, problem scoping. That was us defining our cat versus dog goal. Next up is data collection. That's where we go find all our images. Then comes modeling, the part where we actually build and train the AI. And finally, the big one, evaluation. That's where we test it to see if it learned anything at all. Now, inside that modeling stage, we do something that is absolutely crucial. We take our whole data set and we split it into 2 parts. The biggest chunk becomes the training set. That's the study guide, the open book notes. But the smaller part becomes the test set, and that's the final exam. We keep it locked away, totally hidden from the model until the very end.
So why? Why do we hide that test data? Well, it's to make sure the model doesn't just cheat. We don't want it to simply memorize the answers from the study guide. Think about it. You don't want a student who just crams and forgets everything the next day. You want a student who actually understands the subject, who can take what they've learned and apply it to new problems they've never, ever seen before.
All right, so we've got our data, we've got our process laid out. Now we get to the really cool part. How does a machine actually make the leap from seeing a boring grid of numbers to recognizing a real pattern, like a face or a puppy?
Okay, let's take this image for example. For our brains, this is instantaneous. We see flamingo, water, maybe a mountain, or reflection. Bam, done. It's completely effortless. But for the computer, its journey is just getting started.
And this is what the computer sees. And I'm not exaggerating here. This image was literally made in a Word document just by turning the original photo's pixels into numbers. Each number is just the brightness of one tiny dot. This is the raw clay our AI has to work with. That's it. So the AI's first job is to somehow find meaningful patterns in that massive sea of numbers. The technical term for this is feature extraction. The key is, it's not trying to find a whole dog all at once. No way. Instead, it's learning to spot the little building blocks. Things like the curve of an ear, a sharp corner of an eye, or the unique texture of fur. And here's kind of what that looks like in practice. The AI will run different processes to find all the edges, basically making a rough outline of the dog. Then it looks for corners, because corners are really important points of information. It even analyzes the different textures to figure out what the surfaces are like. It's literally breaking the image down into its most basic visual parts.
So where does all this magic happen? It happens inside something called a neural network. You can think of it as the AI's brain. This visualization gives you a pretty good idea of how it's structured. It's basically a bunch of interconnected layers. As the image data flows through these layers, the network learns to pay more attention to certain features. It figures out that, say, pointy ears are important for cats, and a wet nose is a strong signal for dogs. It's slowly but surely building its own understanding of what makes a dog a dog.
So, after hours and hours of training, going over thousands and thousands of images, it's finally time. Time for the final exam. We take out that test set we've been hiding, the pictures the model has never seen before, and we see if all that studying actually paid off.
And look at this. The results are in. The model takes one look at the new kitten picture and says, yep, 100% a kitten. A perfect score. Then it looks at the puppy and says, 99% confident that's a puppy. It worked! Our model passed the test with flying colors. It actually learned how to see.
And, we don't just have to go on a gut feeling. We can actually measure its performance with real numbers using a tool called a confusion matrix. It sounds complicated, but it's really just a simple scorecard. It counts all the correct guesses and all the mistakes. It gives us cold, hard data on exactly how well our AI did on its final exam.
Okay, but here's where the story takes a really fascinating turn. Everything we've done up to this point, it's all been about identifying what's already there in a picture. But what if an AI could go beyond just seeing and actually start to create?
So the model we just built is what you'd call a discriminative AI. Its whole job is to tell things apart, to classify them. It answers the question, is this a cat or is this a dog? But there's another kind, generative AI, and it does the complete opposite. It learns the patterns of what a cat is so deeply that it can answer a totally different kind of request. Hey, generate a brand new picture of a cat for me.
And this is what that looks like. This incredible image of a teddy bear painting a portrait of another teddy bear. This wasn't made by a person. It was generated by an AI, just from a simple text prompt. This is a machine that has gone way beyond just seeing. You could almost say it has learned to imagine.
And that brings us all the way back to where we started, but with a whole new perspective. We've seen how a machine can go from pixels to patterns to pictures. We've even seen one create something totally new, right out of thin air. So the question really isn't, can a machine learn anymore? The real question is, what should we teach it next?